I'm Shomo Data, and this is Built to Trust. Today, we are going deep on testing that actually earns trust. We will focus on long-duration soaks on observability that tells the truth, and on fault injection you will actually run. We will also tie the whole approach to the systems engineering V, so we verify requirements at the lowest practical level and save time and energy later. The goal is a playbook you can copy into Monday. No theater, no buzzwords, just tests that answer real decisions and keep people safe. You already know the themes of this show. Clarity beats intensity. Cadence turns urgency into sustainable speed. Accountability is keeping promises. Management of change is how we alter a living system without surprises. Today is where those ideas meet the ground. If you cannot observe your system, you cannot trust it. If your tests do not answer a decision, you are rehearsing feelings. If your soak does not run long enough to expose slow burn failures, you are placing a bet with other people's time and safety. Here is how this episode flows. First, what tests are for. Second, observability first. Third, designing soaks that tell the truth. Fourth, fault injection you will actually run. Fifth, a short guide to the systems engineering V and how to use it without jargon. Sixth, an action kit with templates and roles and a simple cadence. Let's get to work. Tests exist to answer decisions. A good test does not prove that we are clever. A good test converts uncertainty into a choice we can make this week. I use one plain sentence before I write any test. Done when X measured by Y observed in Z. X is the outcome. Y is the metric that proves it. Z is where a human can look and see the evidence at 7 in the morning without a tour guide. If I cannot finish that sentence, I am not ready to test. A few examples. We upgrade a parser. Done when throughput holds 30,000 messages per second with 0 parse errors for 12 hours, measured by the error budget and throughput panels, observed in the ingest dashboard. We tighten a hardware in the loop, control loop. Done when the loop stays within plus or minus 2% under worst case timing for 6 hours, measured by loop stability and a jitter histogram, observed on the lab rig. We harden ingest under load. Done when P95 and P99 latency stay under 200 milliseconds for 12 hours with 0 critical alerts, measured by the service health panels observed in operations view. A decision your test should answer might be this: ship now with the guardrail and remove a whole failure class, or defer one cycle and pay down something else first. It might be this: land a thin slice this week and finish the remaining feature next sprint. It might be this: switch libraries now or add back pressure and wait. The key is that your pass or fail gates are numeric and boring. Numbers before adjectives. Pass or fail before narrative. If people have to squint at a chart and guess, you do not have a pass gate, you have a mood. Now, observability first. You will not enjoy a long soak if your system cannot tell the truth under a light. Observability is not an add-on at the end. It is the first test you write. You want to answer 4 questions quickly and without a senior engineer on the phone. Is it up? Is it healthy? What is it doing? When it fails, what fails first? Build 4 simple things. First, golden logs. Keep a small set of canonical inputs and outputs with timestamps and order. A golden log lets you compare before and after and say with confidence that nothing broke at the edges. Second, health numbers that matter. For most services and subsystems, that means 2 or 3 numbers. P95 latency, P99 latency, error rate, retry rate, queue depth, drop rate. Choose the couple that truly reflect user pain and system load. Put them on a panel that everyone can see. Third, traceability across boundaries. Use a request ID, a time base, or a flight number that ties logs and traces and dashboards together. This ends the scavenger hunt. Fourth, back pressure and watchdogs. Your system should tell you when it is at a safe limit, and it should recover cleanly when something hangs. Prove both with evidence. Do this work first. The calm teams I have worked with ship their dashboards and their alerts before they ship features. They want the system to tell the truth during a test and during a launch window. The cost looks high up front. The cost is low compared to an afternoon spent arguing whether a change helped or hurt. Now, soak testing that tells the truth. A soak is a long duration, realistic load run. It is designed to surface slow burn issues you will not see in 10-minute tests. Soak catches memory leaks and file descriptor leaks. It catches queue growth and clock drift. It catches garbage collection thrash and retry storms. It catches tail latency spikes that only show up under spiky jitter. It catches dependency flakiness that looks fine for 10 minutes and fails in hour 12. In hardware or in hardware in the loop, it catches thermal, creep, sensor dropouts, and time-based drift. Soak is where lies go to die. Design a soak to answer a decision and write the pass gates before you start. Use that plain sentence again. Done when X measured by Y, observed in Z, then specify the shape, duration, load profile, environment observability, fault schedule, go or no go, and rollback. Pick a duration that fits the risk you are chasing. 12 hours is a common baseline for software services because slow burn effects usually show by then. For hardware in the loop or integrated rigs, map the duration to your mission profile with margin. Make the reason explicit in the plan. Shape the load like real life. Do not feed pretty averages. Real systems see bursts and idle periods. Real systems see jitter and loss. Shape bursts and shape idle and repeat. For HIL, mirror operational tempos. Push what you will see in the field, not just the mean. Run the soak where timing behaves like reality. For cloud services, that means realistic network behavior and external dependencies. For HIL, that means the rig your operators will use, with the same checklists and interlocks. Build the panels you will screen, capture. Build them before the run. Build the exact graphs you will paste into the evidence pack. Then you will not spend the next morning digging through logs to tell a story. Plan 2 or 3 faults you will inject during the soak. Kill a process, introduce jitter, skew a clock, flap a dependency, drop a sensor. The aim is not chaos for its own sake. The aim is to prove that the guardrails you claim actually work and that the alarms you set actually tell the truth. Write one boring paragraph that defines go or no go and rollback. For example, we go if P99 latency stays below 200 milliseconds for the full run and there are 0 critical alerts. We know go if we see 2 watchdog events or if queue depth holds above threshold for 10 minutes. Decider is the test conductor. Rollback is build 413 within 10 minutes with a clear step-by-step procedure. When this is written before the run, people argue less and execute more. Make pass gates numeric and boring. P95 and P99 latency stay within spec for the full duration. No monotonic resource creep beyond thresholds in memory or threads or file descriptors or disk. 0 critical alerts. Recovery on restart or rollback within the target time. Golden log diff shows no parse or order regressions. Back pressure engaged under load and shed safely. For HIL, loop stability stays inside the band. Time-based correlation is within tolerance, and sensors and actuators stay within spec. Tell the story with pictures more than adjectives. A handful of screenshots and a single page of verdicts should let a teammate nod and say, yes, that is true. You want a snapshot of each health panel at start and midpoint and end. You want a trend screenshot for any metric that drifted. You want a short note for each injected fault and what you saw. You want a one-line verdict for each pass gate. Keep cost in check. Reuse the same harness across services. Copy the same dashboard and rename the panels. Automate pass gates where you can. Schedule soaks in windows where real people can observe without hurting their sleep. Assign a scribe so engineers do not spend a morning formatting evidence. Now, fault injection you will actually run. Many teams treat fault injection like a carnival you hold once a year. That is theater. Put 2 or 3 faults inside every soak. Schedule them. Observe the system as it recovers. Pick faults that match your hazard list. Kill a process. Does the watchdog restart cleanly, and does the system rejoin without corruption? Introduce network jitter and loss. Do your clients back off, or do they stampede? Skew a clock by a minute. If your parsing or your signing or your ordering relies on tight skew, find out now. Fill a disk to a high watermark and to full. Do you alert early enough? Do you enter a safe mode or fail messily? For HIL, heat and cool, within operational bounds and look for drift. Flap a partner API. Does the system reconnect and drain queues? Drop a sensor reading to 0 or inject an out-of-band value. Does your estimator degrade gracefully? Faults do not need to be exotic. The best test teams I know always run a few simple faults and one guarded spicy one. They choose the ones relevant to this decision. They prove them. Then they move on. Now the systems engineering fee, without jargon, the left side is decomposition into requirements and design. The right side is integration and validation. The bottom is verify at the lowest level with the cheapest method that still tells the truth. The rule that saves labor looks like this. Verify each requirement at the lowest practical level. Validate at the top that the system as a whole meets the mission need. Map each requirement to a verification method and to a lowest level. The methods are inspection or analysis or demonstration or test. The levels are component or assembly or subsystem or interface or system. Prove the requirement early at that lowest level. Use component analysis, unit tests, simulation, bench tests, HIL with stubs or contract tests for interfaces. Then confirm composition up the right side and validate that the full system meets the need. Interfaces deserve special attention. Many failures hide at seams. Write a contract test at the boundary. Soak the interface under worst case patterns. Keep golden logs at the boundary. Here is a simple example. Requirement ingest P, 99 latency under 200 milliseconds for 12 hours with 0 critical alerts and loss less than 1 in 10,000 and rollback under 10 minutes. Component level. Prove parser performance and garbage collection behavior under replay logs. Subsystem level. Run a 12-hour ingest pipeline soak under worst case jitter. Prove watchdog and back pressure. Prove 0 critical alerts and loss rate within budget. Confirm golden log parity, system level. Run an end-to-end soak with a failover drill. Validate that the behavior meets user expectations. The heavy lifting is done low. The welds are confirmed up the right side and the validation is calm. Use cheap methods when they are enough. Inspect dimensions and labels. Do not write a test for something you can verify by looking once. Use analysis when physics rules. Use demonstration for human procedures. Use test when behavior under uncertainty matters, and always maintain two-way traceability. Requirement to test, case to evidence. Test case back to requirement. Then when someone asks why a test exists, you click a link, not write a speech. Let's move to the action kit. Here is a soak plan you can copy. Objective, what decision will this soak answer? Load profile, shape, average and burst and idle and burst. Jitter bounds, dependency behavior, fault schedule. The 2 or 3 faults and when we will inject them. Duration and environment. How long? Why that is representative. Where it runs. How the environment mirrors reality. Metrics and dashboards. Health numbers, P95 and P99, error rate, retry rate, queue depth, drop rate, CPU, memory, threads, file descriptors, disk, which panels we will snapshot, pass and fail and rollback, numeric pass gates, early abort triggers, decider, rollback steps and target time, communications, who knows before we start, live update cadence during the run, where results will be posted, owners and roles, driver, approver, test conductor, data scribe, environment owner, on-call backup. Here is an acceptance checklist. P95 and P99 within spec for the entire duration, error rate within budget, no critical alerts, warnings are expected and documented, no monotonic growth past thresholds in memory or threads or file descriptors or disk, back pressure engaged under load as designed, watchdog events 0 or within allowed budget, golden log diff shows 0 parse or order regressions, rollback or restart tested, recovery within the target time with evidence. For HIL, loop stability and band, time-based correlation within tolerance, and sensors and actuators within spec across the profile. A small catalog of faults to schedule. Kill and restart a process or container. Introduce network jitter and loss within bounds. Skew one node's clock by a fixed offset. Fill disk to a high watermark and simulate full. Spike CPU or throttle it. Flap a dependency and vary the error type from fast fail to hang. Drop a sensor reading and inject an out-of-band value. For HIL, power cycle the rig with proper safety observers. Minimal dashboards to build once and reuse everywhere. Throughput over time with markers for faults. P95 and P99 latency over time with thresholds visible. Error and retry rate over time. Queue depth and back pressure state over time. A resource panel with C, PU, and memory and threads and file descriptors and disk. An alerts panel with counts for critical and warning. For HIL, a loop stability band and a time-based correlation panel, and sensor and actuator monitoring panels. Name 3 hats for any serious run. Test conductor, safety officer, data scribe. The test conductor owns the timeline and calls the faults and makes the go or no-go call using the paragraph. The safety officer watches risk and people and can halt the run. The data scribe captures timestamps and screenshots and fault notes and assembles the evidence pack so engineers can keep working. Create a one-page runbook header for the SOAK, name, owner, last updated, last dry run, escalation ladder with contacts, rollback steps, store it where work happens, dry run the runbook the day before with someone who did not write it. Every significant change that your SOAK informs gets a small decision log entry, 5 lines. The decision, the date, and the decider, the options you considered. Why you chose this one, a review date if you intend to revisit, links to the SOAK plan and the evidence and the requirement. This is how you avoid fighting the same battle next quarter when a new person joins the thread. Tie all of this into a 6-week cadence so testing is not a side quest. Week 1, write the SOAK plan, build or update dashboards, dry run runbooks, schedule the environment, write the go or no-go paragraph. Week 2 or week 3, run the SOAK, inject the faults, collect evidence, post 2 truths and 1 risk as you go. Week 3 or week 4, assemble the evidence, write the 1-page verdict, update the decision log, ship the change or adjust plans. Week 5, hardening week, turn SOAK insights into guardrails and refactors and rollback improvements. Update runbooks. Week 6, demo the truth, hold a retro, close the loop on actions in front of the team, update the baseline. Now a few anti-patterns and how to fix them. Happy path demos. Everything looks great in a 10-minute rehearsal. No one runs long. Fix. Write a SOAK gate for every demo that matters. Rehearse with the same harness. Band slide only passes. Present numbers and evidence. Observability last. People argue for an hour about whether performance regressed. Fix. Build the dashboard first. Define a couple of health numbers. Prove pass or fail with pictures and a golden log diff. Test plan after the work. You cannot tell what you proved or why it matters. Fix. Write the decision and the acceptance before you build. Treat the SOAK plan as a small contract. Interfaces untested. Unit tests are green, but integration fails under real timing. Fix. Write contract tests at seams Soak under worst case patterns. Add a golden log at the boundary. Works on my rig. Timing or environment issues pass locally and fail in the field. Fix. Specify the test environment. Move verification to a shared realistic environment. Rehearse in the same context you will ship. Fault injection as a carnival. You do chaos day once and forget. Fix. Put 2 or 3 faults into every soak. Schedule them. Prove recovery, no rollback. When things go wrong, people improvise. Fix. Write a rollback plan into the soak plan. Test it. Set an early abort trigger. Protect freeze windows. No traceability. Someone asks why you shipped and the room goes quiet. Fix. Link requirement to test to evidence to decision. Store it where work lives. A few short stories. A data service kept missing its service level objective under jittery traffic. Every Friday, alarms fired. On-call sprinted. Leaders talked about accountability. It was theater. We wrote a simple soak plan with a worst-case jitter profile. We added back pressure and a proper watchdog. We ran a 12-hour soak with a fault schedule. We proved that the old library hung under a specific timing pattern. We replaced it. We proved the fix with the soak. We removed an entire class of incidents. Friday stopped being a ritual of suffering. A test harness skipped a step under certain timing. Everyone knew it was considered fine. A small fix looked like a low-tier change. The blast radius said it was a medium tier because the harness fed 3 subsystems. The owner wrote the change note, added checksums, and ran a soak with a fault simulation. The deploy was boring. 2 months later, we did not spend a week chasing a ghost. Boring is a compliment. We once got lucky. An external dependency woke up fast all week. A fragile interface looked stable. The demo felt great. In the retro, we asked, if the wind were neutral, would we still land? The answer was no. We added a guardrail and a soak with worse timing. Luck stopped being a dependency. Coaching managers matters. Testing must be a leadership habit, not a last-minute panic. Here is the routine I coach. Write the decision and pass gates in the weekly intent. If you cannot say, done when X measured by Y, observed in Z, you are not ready. Do 1 floor walk in logs or on the rig. Ask, if this failed now, how would we know? Show me the runbook we would open. Close 1 decision and log it in 5 lines with a link to evidence. Touch 1 runbook. Update the header. Do a dry run. Fix 1 step. Celebrate 1 boring test that passed on purpose. Make testing prestigious, not a chore. Remote and hybrid runs work fine with a little structure. Use 1 channel for live updates with timestamps. Ask the scribe to post screenshots as they come. Record short screen captures at the end of each phase that say, here is what we just observed. Store the evidence pack in the same place every time with the same structure. Distance is not the enemy. Ambiguity is. Tie back to management of change. A soak is premium evidence for a change note. When the owner writes that we will replace a client library because the old one hangs under jitter, the soak plan and the pass gates are the proof. The go or no-go paragraph for deploy came from the soak. The rollback steps were rehearsed. Freeze windows are easier to defend when you show evidence. The same rules apply. The test conductor is the owner during the run. The safety officer watches people and risk. The approver signs off because the evidence is right there. Common questions. How long should our soak be? Long enough to expose the slow burn risks you suspect, and not an hour longer. Start with 12 hours for most services. For HIL, tie duration to emission profile plus margin. If you do not know, start with 6. If you see no creep, pick the next higher risk and design for that. What if we cannot simulate the full environment? Simulate what you can and be explicit about what is fake. Use fault injection to stress the seams you cannot simulate, and then get a small window in the real environment for a targeted soak with narrow scope and high observability. What if an SLO is new and we do not know the threshold? Pick a hypothesis. Put a review date in the decision log. Collect data. In 2 weeks, revisit and adjust. It is better to be explicit and wrong for a short time than to be vague forever. We work in a regulated domain. Will this pass audits? Yes, if your traceability is clean. Your requirement, your test case, and your evidence pack are the artifacts auditors want. Your change note and decision log tell the story of control. Smaller and clearer passes faster than longer and vaguer. A compact checklist you can start this week. Write a 1-page SOAK plan with a decision and numeric pass gates. Build the minimal dashboards and the golden log diff. Add a short fault schedule to the plan. Name roles, test conductor, safety officer, data scribe. Run the SOAK in a window where people can pay attention. Update the decision log with a 5-line entry and links to evidence. If you ship, update runbooks and on-call training. If you do not ship, write a change note for next cycle with the guardrails you will add. Testing is not an exam you pass. It is how you talk to reality. When you write pass gates in numbers, your team argues less and ships more. When you instrument for truth, your SOAKs take hours to interpret, not days. When you verify at the lowest practical level, integration becomes a confirmation, not a rescue mission. When you inject faults inside SOAKs, your guardrails either work or they do not, and you learn while you can still act. When you bring all of this into your cadence, testing becomes a boring habit. Boring is a compliment. If this helped, follow Built to Trust wherever you listen. Hit subscribe. Share it with a teammate who lives in test rigs, on call rotations, or release trains. Your ratings and reviews help more builders find the show and build with more truth and less drama. Next week is episode 9, Roadmaps That Ship. We will translate strategy into plans that respect physics. We will set capacity and WIP limits. We will say no without burning trust. We will connect intake, change notes, freeze windows, and decision rights, so your roadmap becomes a schedule of real landings, not a deck of wishes. I'm Shomo Data. Thanks for listening.